Imagine sitting down to a hot bowl of soup. You drop your metal spoon into the broth, get distracted for a few minutes, and leave it sitting there. When you finally reach back to take a bite, you grab the handle and immediately feel a sharp burn, yanking your hand back in pain. But consider the handle for a second. It was sticking up in the air, never actually touching the hot liquid. So how did the heat get all the way up there to burn you? The heat traveled directly through the solid metal of the spoon itself. This is the physical process of thermal conduction. While convection circulates heat through liquids and gases, and radiation beams it across empty space, conduction is the undisputed champion of heat transfer within solid objects. It follows one strict rule. Thermal energy always flows from a region of higher temperature to a region of lower temperature. To actually see this invisible energy transfer in action, we have to look past the everyday human scale and shrink all the way down to the microscopic building blocks of that spoon. Down here, what looks like a rigid, stationary piece of metal is actually a hyperactive highway for thermal energy. Every solid object is made of tightly packed atoms or molecules. They are locked into a grid, but they aren't completely still. They have a constant slight vibration. When you plunge the bottom of the spoon into the hot soup, those specific particles absorb thermal energy. They start vibrating violently, swinging wider and faster until they physically crash into the layer of particles directly above them. Every crash transfers that kinetic energy up the line. The heated particles smack into their colder neighbors, making them vibrate wildly, which makes them smack into their neighbors, cascading upward like a microscopic row of falling dominoes. The thermal energy travels all the way up the spoon to burn your fingers, but the actual particles never leave their fixed positions. This brings up a question. If you left a wooden spoon in that exact same soup, you could grab the handle 10 minutes later without feeling a thing. Different materials play by different rules. Metals are excellent conductors because they have an atomic advantage, a sea of free electrons. These tiny, negatively charged particles aren't tied to any specific atom, acting as high-speed express lanes that carry thermal energy across the material almost instantly. Insulators, like wood or plastic, lack these free electrons. Their particles are tightly bound together. This forces the energy to crawl upward through clumsy, slow atom-by-atom collisions. The invisible microscopic structure of a material entirely dictates whether it acts as a rapid thermal conductor or a stubborn insulator in the real world. We can prove this invisible wave of kinetic energy exists using a classic physical demonstration. If you take a metal rod, attach a line of nails using wax, and heat one end, you can watch the conduction happen. As the heat wave travels down the rod, it will melt the wax and drop the nails in sequential order. The speed of those falling nails is directly tied to the temperature difference. A much hotter flame applied to a colder rod will drive that heat wave down the line even faster. What you are watching is the macro-scale shadow of those microscopic collisions, happening billions of times a second inside the solid metal. There is a common misconception about these stubborn materials. Many assume a thick piece of wood or plastic acts as an impenetrable wall that completely stops heat in its tracks. In reality, if an insulator is exposed to a heat source for a long enough time, those slow, clumsy vibrations will eventually reach the other side. Insulators do not stop thermal conduction. They merely slow it down to a crawl. Understanding how to control that speed gives us everyday tools. A metal cooking pot with a thick plastic handle is the perfect marriage of a rapid conductor for the food and a protective insulator for your hand. We also rely on rapid conduction to survive the cold. A traditional bukhari, a cylindrical metal room heater used in the Himalayas, is built entirely out of conductive metal to aggressively pull heat from a wood fire and push it out into a freezing room. Conversely, when we step outside into that freezing air, we wear thick winter coats. These garments trap pockets of air, a notoriously poor conductor, to slow down the escape of our own body heat. Every time you grab a hot mug of coffee or pull on a winter coat, you are physically interacting with millions of microscopic collisions, turning an invisible law of physics into a tangible reality.